In this video, we're going to take a look at uniform and continuous mass distributions. And you will have learned a similar procedure in your multivariable calculus class. But what I'm about to show you is probably going to be a little bit different. There tends to be some differences between how things are done in math versus how we do them in physics. Technically, there's nothing wrong with either approach, but there are differences. And so this may look very similar but different, or you may automatically be able to make it right and reconcile the differences in your own mind. So the first thing that I want to talk about is going to be the mass densities that we've done before. This is particularly important in this particular topic. And so the one that's going to be of most value to us is going to be lambda. So lambda is equal to the mass per unit length. And the big thing is with center of mass is when we see the equation, it's an integral with respect to dm, and that's going to cause us some problems. And so the critical step is going to be converting dm to a dx, or a dy, or a dz, or a dr even. But when we get there, I'll explain that a little bit more. But just remember that if we break up this mass per unit length into smaller and smaller pieces, what we end up with is a little delta m over a delta L, and if L is in the x dimension and we take this in the limit so that these pieces get infinitely small, we just end up with a dm dx or a dm dy, dm dz. Okay, so that's going to be critical in doing these problems with center of mass. Now, the other thing that I want to talk to you about before we actually get into a problem is the various ways of representing center of mass mathematically. You'll find in your textbook on the AP equation sheet that center of mass is often listed as xcm is equal to 1 over m times the integral of x dm. And so let's just take a look at this for a minute and explain some of our complications. At first glance, determining the center of mass using this equation appears to be very straightforward. You integrate with respect to dm, and x is going to just come out as a constant, and so you get, the integral of dm is just m. But the problem with that is when we look at how this is set up. Okay, so this is just for a long thin rod, if you will. And when we integrate this, we're integrating with respect to position, or dx, because we're going to take this small chunk that's right here, and then we're going to add to that this small chunk that's right here, and this small chunk that's right here. So if you recall, when we look at discrete particles, we had xcm was equal to m1 x1 plus m2 x2 over m total. And that's what we're doing here, but we're integrating across a length dimension, not across a mass. Okay, so we're going to go from, like in this example, we'll be integrating from 0 to L. That's what we have to integrate with respect to. So it's a length dimension. So this dm is going to have to change. And that's what all this stuff up here was for. And we'll get to that, like I said, in just a couple of minutes. But this is only one representation. But given that, you all take multivariable calculus and you are a little more sophisticated, I did want to show you some other representations that you may find actually more helpful. The problem with this particular representation is that if we write this as 1 over m, then the assumption is that it's a uniform distribution, and that's okay. I mean, many of the problems that you would have to do for the AP exam, for example, that's going to be a true statement. All of the problems, that's the way it's going to be. However, in class, I'm going to, of course, push you to go further than that, so that when you are required to do things on the exam, you don't struggle with what should be relatively easy problems. So we need to rewrite this. And the way we're going to do that is we're going to write it as xcm is equal to, and instead of having this as a 1 over m, we're going to put it into a form that allows us to add up all the little pieces of mass dm. Okay, so our center of mass equation becomes the integral of x dm over the integral of dm. And that's what we're going to use for our center of mass equation, in particular whenever we have a non-uniform mass distribution. Okay, so let's go ahead and get started with our particular problem here. And in this problem, we're going to start with the traditional equation. So we're going to start with that one. We're just going to say xcm is equal to 1 over m times the integral of x dm. Now, as I've already said, we're going to basically be integrating from where x is equal to 0 all the way down to the point where x is equal to L. So our limits of integration go from 0 to L. All right, this is a uniform distribution. This is going to be an object which has a mass of m. And so we just have to figure out how the heck we're going to integrate this with respect to position whenever it's right now being integrated with respect to mass. So that's where this expression comes in up here. Lambda is equal to dm dx. And so dm is going to be equal to, or let's do it this way. We have lambda is equal to dm dx. So dm is equal to lambda dx. So we'll make that substitution, and we have xcm is equal to 1 over m times the integral from 0 to L of x lambda dx. Now lambda is going to be a constant, so we can pull it out, and we get xcm is equal to lambda over m times the integral from 0 to L of x dx. And when you integrate that, we get lambda over m times 1/2 x squared, and then we evaluate that from 0 to L. All right, so xcm is equal to lambda over m times 1/2. Now we put L in for x, so we get 1/2 L squared minus lambda over m times 1/2 0 squared. So of course this term here is going to go away to 0. Now at this point, this does not look like we have been able to show that the center of mass is at the geometric center. Remember, geometric center is going to be 1/2 L, so we expect xcm to be equal to 1/2 L. That's what we want, and we've not shown that yet, but the problem is this lambda. So as soon as we convert lambda, everything falls into place. Now lambda, we know from earlier, is just equal to mass per unit length whenever it's a uniform mass distribution. So we can write lambda as m over L, and then we just have this times the 1 over m times 1/2 L squared. And so now we get one of our L's here cancels with this L, this m cancels with that m, and we're just left with xcm is equal to 1/2 L, which is exactly what we expected. Now, there is a slightly alternate version of solving this, and so I want to take a look at that now. In this case, we used the AP equation, form of the equation, for determining center of mass, but I want to use this other equation here because you might find that it's a little bit less troublesome for you. For example, you might forget about that lambda and how to deal with it. Okay, so if we take a look at it from this approach, then what we end up with is xcm is equal to the integral of x times, now remember, dm we just said was going to be equal to lambda dx. So this becomes x lambda dx, and then we divide that by the integral of dm, where dm is still lambda dx. And so now we can see that lambda is a constant and that we can just cancel it out. It's no longer a problem for us. And we get xcm is equal to, now the integral of x dx is 1/2 x squared evaluated from 0 to L. And then we divide that by the integral of dx, which just gives us x. And so we can cancel one of the x's from the numerator with the denominator, and we're left with xcm is just equal to 1/2 L, which again, this is what we expected.